Okay, so welcome to Math 313 number theory. This should be lecture 26. What I want to do is we're going to go and do elliptic curves, which is a natural way to build on what we were doing, looking at the circle, counting points on that, trying to find solutions to Pythagorean equations. But I wanted to first jump a little bit to some dynamical systems. I'm going to do a little bit of the material that's in chapter 10, I think, but I also wanted to deliberately do some material that's not in chapter 10 to just give us another example to try to do some coding in real time and to give you an opportunity to conjecture. So you probably have noticed there hasn't been that much of a homework assignment this week. What I really want you to do is think a little bit, tonight and tomorrow about what you think might be true about this problem. If you have seen this problem before, you are not eligible to speak up and conjecture right now. So how many of you have heard of the Collatz problem? Okay, how many of you have heard of the Syracuse problem? How many of you have heard of the 3x+1 problem? Okay, they're all the same problem. This problem has lots of different names. My two favorite quotes about this problem is one by Paul Erdős, "Mathematics is not yet ready for problems like this." And the other is from Kakutani, who described this problem as a Soviet conspiracy to slow down American mathematics, because every time he traveled to a new school, he would talk to some of the people there and say, "Oh, that's not that bad," and they'd start working on it, and then in about a month of frustration, they would stop. And so it's amazing how many people have worked on this problem over the years and how much good mathematics is connected to this. So a lot of times you look at it and go, who cares? Well, it turns out the resolution of this problem is related to a variety of things. So I will use the name 3x+1, but it does have other names. This is something that could be done in high school, could be done in junior high school. So I'm going to define a sequence. We've done sequences all the time. Here's the rule. an plus 1 is going to be 3an plus 1 if an is odd, or an over 2 if an is even. So this is the standard definition. Okay? There's another tweak that you could do. An alternate definition is you could say, say bn plus 1 is 3bn plus 1 divided by 2 to the L, where bn is odd, and so have you ever seen this notation, double divides? So this is great notation. What do you think 2L double divides 3bn plus 1 is? Yeah.
It divides it even when you can't put any more factors.
Yeah, you can't put any more factors. So for instance, 2 divides 16, but so does 4, so does 8. So this is the highest, that I will get. So what I'm basically doing is, look, if the function is odd, I multiply by 3 and add 1, and then if it's even, I pull out some 2's. Why not just do this all in one step? It turns out that depending on how you want to analyze it, sometimes one viewpoint is better than the other. When you're trying to count how long does something take. Now, who has heard of this problem? Who has heard of this sequence? Okay, so there's a specific number I don't want you to say right now. Okay? So if you know this problem, you might know the specific number I don't want you to say. Somebody give me a reasonable number, a reasonable integer. 12. Okay, so let's see what happens if we iterate 12. 12 is even, goes to 6. 6 is even, goes to 3. 3 is odd, goes to 10. 10 is even, goes to 5. 5 is odd, goes to 16. 16 is even, goes to 8. 8 is even, goes to 4. 4 is even, goes to 2. 2 is even, goes to 1. I'm running out of space. I hope I'm still being recorded. Fortunately, at this point, what does 1 go to? Okay. So we have a trajectory. So 12 was our starting seed, and this is the evolution. Somebody give me another number. If you wanted to be kind to me, what number would you give me right now? Yes, something on that line. If somebody wants to get some brownie points with their professor, say 10 or 5 or 16 or 3. Make my life easy, right? But this is Williams. We like a challenge. Somebody give me another reasonable number.
The smallest number not on the line is 7.
Ah, smallest number not on the line 7. That's a great thing to try. So 7 is odd, goes to 22. 22 is even, goes to 11. 11 is odd, goes to 34. Big Poppy. 34 is even, goes to 17. What does 17 go to? 52. 52 is even, so goes to 26. 26 is even, goes to 13. 13 is odd, goes to 40. 40 is even, goes to 20. 20 is even, goes to 10. Okay. What might you conjecture? And if you've seen this problem, you're not allowed to conjecture. Yes?
Every number eventually goes to 1.
Every number eventually iterates to 1. We have a lot of data points here. Right? How many of you are comfortable with this conjecture that it always goes to 1? No one's very, I saw like one hand kind of going. I saw one smile. Yeah, this is being recorded. I will say it always goes to 1. Proof pending. Right? This is the 3x plus 1 conjecture. No matter what integers you start as your seed, you will eventually iterate to 1. Okay? So what I want to do now, let's see. Okay. So let's see if, I'm just curious to see if this type's well enough to be visible. Or if I erase this, it might become an enormous problem. So we'll see. Oh, it's actually erasing fairly nicely. Okay, so maybe this will work. So it's not unreasonable to conjecture, based on what we've seen, that we will iterate down to 1 eventually. What other questions might you ask related to that?
How fast do you get there?
Yeah, how fast do you get there? So let's go to format size. How fast does it take to iterate to 1? Okay, so hopefully that's readable. That seems like a very reasonable question to ask. How would you try to go about answering this? Yeah?
You can make a computer program to just like see what the distribution is.
Right. This is one of the reasons I'm always yelling at you. Program, program, program. Gather data. The question is always, when do you think you're going to have enough data to be confident? So one of the things, next year I'm teaching advanced applied analysis. I think that's what we eventually called the class. One of the things we're going to be talking about is Benford's law of digit bias. In a lot of data sets, it turns out that the first digit is 1 more often than you might expect. So in 2017, the first digit of 2017 is what? Oh, come on. I'll do it this way. So what's the first digit in 2017? 0, right? This is not that bad. This is who's awake right now. So if you looked at a lot of numbers in a lot of data sets, if everything was evenly distributed, how often would you say the first digit should be a 1? Those who've had me in probability are not allowed to answer right now. If you would just guess, naively, what would you guess? What percent of the time would your first digit be a 1? 1/9. So you're being too smart. If you weren't as smart as you are, what would you guess? You'd guess 1/10. All the numbers are equally likely. And then you realize there's only one number that has a leading digit of 0, and that's the number 0. If I give you point 0.00045, that's the same as 4.5 times 10 to the negative 4, right? And so the leading digit of that would be 4. So you would correct from guessing 1/10 to guessing 1/9. It turns out about 30% of the time your first digit will be 1 in a lot of data sets. About 4.5, 4.6 of the time, it'll be a 9. The IRS uses this to detect tax fraud. Fortunately or unfortunately for individuals, there's not enough data points on your tax returns for them to use this on you, but there are enough on major corporations. The biggest question the IRS has is, when do you have enough information to be suspicious? How much data is enough? How quickly does this bias set in? So when we're looking at 3x+1, when we're trying to figure out what's going on, the natural question is, how many data points do we need before we can be confident that we're sniffing out how fast it iterates to 1? It's always a question of what is the correct scale. For a problem like this, how big of a number do you think you need to investigate to be confident? If we investigate all numbers up to 100, are you confident? So what do you think? Up to 100? Yes or no? No. Actually, as long as I'm writing this much, I might as well put that on the screen. All right, so we're not too confident if we just go up to 100. All right? All right? What about 1,000,000? Would you be confident if we looked at the first 1,000,000? Do you think the pattern would set in by there?
Kind of, as you go to higher and higher numbers, you should have higher and higher, like, it should take more and more iterations to get to 1.
Mm-hmm. So we've talked a little bit about this, earlier in the semester when we counted primes up to 10, and then primes. Oops, too many m's. Primes up to 20. And so the primes up to 10, well, I don't know why it's trying to fix this. Wow, all right. That, I guess, was too much for Mathematica to deal with. All right, so all right, so let's try this again. All right. Is it too high up? No, that's okay. So primes up to 10, primes up to 20. And let's make it large again. Okay. So the primes up to 10 was 2, 3, 5, and 7. 11, 13, 15, sorry, not 15, 17, and 19. So we saw 20% of the numbers started at twin prime pair. We saw 40% were prime. So 20% twin prime pair, 40% were prime. Do we expect these patterns to hold? No. What's the right scale to be looking at primes? So we've talked about this a couple of times. Yeah?
You do like 2 to the n or something?
Okay, so
Like, look at all primes, figure out how many primes are less than like a certain like value at 2 to the n or something.
okay, and so I'll extract from that a log scale. That if we look at primes up to x, the average spacing up to x. So average spacing up to x is log x. So when we're trying to figure out how far to go, the average spacing between primes is growing very slowly. So in order to be able to go far enough to see something, going up to 10, 20, even up to 1,000,000 is not going to be enough. Anybody know roughly what the log of 10 is base e? Roughly. A little bit more than 2. E is less than 3. So e squared is going to be less than 9. E cubed is going to be greater than 10. So it's somewhere between 2 and 3. Log of 10 is about 2.3. So if we have 1,000,000, 1,000,000 is 10 to the 6. So the log of 1,000,000 is about 6 times 2.3. That's under 15. We're not going sufficiently far to really see much. If I now go up to, let's see, skews number. This is one of my favorite numbers in all of mathematics. For a while, this was the largest finite number that occurred in mathematics in a meaningful way. So it is the first number such that the number of primes up to x is larger than the main estimate. Li of x is the logarithmic integral. It's the integral from 2 to x of dt over log t. So it was observed that in numerical tables of primes that this formula always seemed to overestimate the number of primes. So eventually people conjectured, well, maybe it always overestimates. And it turns out if it always overestimates, you can prove the Riemann hypothesis. Skews had a brilliant argument to get it down. So his advisor, Littlewood, was the first one to show that they actually flip infinitely often as to which one is largest, but didn't bother to figure out where the first flip was. So this is a good job for a graduate student. So Skew's job was to figure it out. And so Skew's proof has two parts. Part 1, assume the Riemann hypothesis is true and get a bound for the first flip. Part 2, assume the Riemann hypothesis is false and we have an exception, and use that to get a bound for the first flip. And so he showed that if the Riemann hypothesis is true, then there's a violation before 10 to the 10 to the 10 to the 34. So I can write a number like 10 to the 10 to the 10 to the 34, but this is not meaningful. If you can process the size of a number like this, please tell me how. This is just beyond what most of us can do. There's about 10 to the 80 objects in the universe, maybe 10 to the 90, somewhere in that range. So if you think of just 10 to the 34, 10 to the 34 is significantly less than the number of objects in the universe. But now if I have 10 to that, I mean, this is astronomical, and then I still have one more 10. He showed if the Riemann hypothesis I think this is with it's false, but it's phrasing a little bit different. He got 10 to the 10 to the 10 to the 964 the other way. And so it's now been shown that it got down to around 10 to the 1165. Now they've got an upper bound of 10 to the 370. But it's an extremely large number. And so the problem with stuff like this is that where the action is happening is often well beyond what we can investigate. So the question is, how do you get meaningful data? How would you investigate numbers that are this enormous? So the first thing is, let's just talk about 3x plus 1, and let's just try to figure out how to do it for reasonable numbers. So the first thing is, we would want a function that would define the next term. So there are two ways we can do it. We can remove all the powers of 2 at once, or we could, if it's odd, do one thing, and if it's even, do another. Which do you think is going to be easier? I'm sorry? About the same. I know for me, if I'm a young coder, one seems easier than the other. I think it's easier to split it up and do even odd. So let's do the 3x plus 1 function. Okay, so the first is, let's define f of x as follows. If well, I'll try to fix it in a second. If mod x2 equals 0, so if it's even, what should it be?
I think you can.
Is there a way to just globally change the size?
I think you go to window, and then it might have a magnification. Yeah.
Oh, okay.
And then you don't bother.
Right, and then I'll just change this back to normal. Thank you. So here, I think, yeah, but it's shifting over, unfortunately. All right, well, it's still better, I think. 3x plus 1 function. So we'll just have everything shifted over a little bit. All right, so we could define f of x if mod x2 is 0, so it's even, what should it be? X over 2. And if it's odd, We can just do 3x plus 1. And that's the function. What would we do if we wanted to pull out all the powers of 2 at once? So it would be a more complicated function. And again, when I'm coding, and it's been a while since we've done coding, that's why I want to do some today. Whenever I begin something, I want to immediately end something. So module is how Mathematica does a function. I've begun it, I want to end it. So what I'm going to do is assume that I always put in an odd number. You could, of course, create your function to be a little bit better so that if somebody is an idiot and puts in an even number, it will print out a warning message. That's better coding. You don't want things to just keep computing garbage. I will assume that whenever I use this, I'm smart enough to make sure that I don't put in an even number. It'll allow me to run a little bit faster because I don't have to do that check. It's not that bad of a check to do, but let's just assume we're good. All right. So I will write over here, input is an even number. So what's the first thing we should do? Our temp number is going to be what? Three x plus 1. So we first multiply by 3. And then I will say this in the killer directory. 3x plus 1 Math313 code. Okay, so now what do we need to do? We need to remove all the powers of 2. Anybody know a good command structure to remove powers of 2? Yeah, while loop. While mod temp 2 is even, what should we do? Temp equals temp divided by 2. And that should just keep removing powers of 2. And then return temp. So those should be the two different codes. We'll probably reduce the magnification just a little bit. Is that still very visible? Okay. So now we've got our functions defined. So we can now define a iteration function that will iterate until we get all the way down to 1. So we have two different ways to iterate. We can iterate with f, we can iterate with g. So, iterate f, we have some input, module, and then the question is, how do you want to do this? One thing is, do we want to save the values? Do we want to just print out the values? What do we want to do? So one possibility is we might just want to count the number of steps. So if all we care about is counting the number of steps, then we don't have to save things into a list. Why might it be dangerous to save things into a list? No idea how big that list is going to get. And as you save things, it takes more and more memory, and Mathematica and a lot of programs start to slow down as you keep all these things in memory. If you really cared about things, what you might be doing is maybe saving it to a file as you go and not keeping it live in memory. These are things that become extremely important. If all you care about is the number of iterations, and you don't care about the list, then we can just do a count. So what we can do is maybe count is initially 0, and then start. Well, we'll do the current number will be x, and then maybe while current is greater than 1, what should we do? Not g of x based on how I've defined this function with the name. Well, that would be calling the function inside itself. I can't set x equals f of x because x is the input that we put in. I can set current. This is why I have to define a new thing called current. I can't change x. So what I can do is I'll call it maybe start. So this is the start number, this is the input number. I can't override it. That's being passed in as a value. So I choose a new variable called current, and I assign current to be the start value. And then what I'm going to do is I'm going to just apply the function f to current, and that'll give me the next term in the sequence. And what else do I have to do at the same time as I apply f? Increase the count. So while current is greater than 1, begin and end. So this is end of while loop. Current equals f of current, and then count equals count plus 1. And what I'm going to do now is I'm going to do print current. Although actually, where should we print current? We should print it actually before we iterate. Well, we'll iterate here, and then what we can do is print. We are starting at current. And I'm going to add an additional condition here, print. And so I actually love doing something like this. What I'm going to do over here is I'm going to say if print equals 1, this is an old keyboard and it clicks a lot, then I'm going to print current. So what I can do now is I have one program, and if I pass in a value of 1, it's going to actually print out the sequence of numbers as I go. And if I pass in anything other than 1, it won't print. If I'm trying to do things efficiently, is this a good line of code to have? What I'm going to have to do then is every time I go through the while loop, I'm always going to have to check and see, does print equal 1? But this is such a fast thing to check relative to all the other stuff that I don't think you'll see a real slowdown because of this. So let's see if this works. Then the other thing, of course, is whenever you write code, you always want to be constantly saving it. So we've defined our function f. Everybody happy with this? So let's run it. So iterate. I think 10 was one of the things we gave. Oh, iterate f10. Oh, I have to put in 2 values. And let's print things out. So here we go. We started with 10. We went down to 5. All right, so it's not printing out the current value. That's interesting. Oh, no. Oh, okay. We're starting at 10, and then this is the next value. 5, 16, 8, 4, 2, 1. So if we chose another number like 17, here's our chain. Yeah. Oh, we should probably print out, we absolutely should print out the count at the end, you're right. That would be a good thing to know. Print number of steps to reach 1 is count. Now, what is this program assuming? That I will reach 1. If I don't reach 1, I never get to that line. But it's very good to print out the object we want to find. Years ago, I was doing some research in additive number theory on something called more sum than difference sets. And I was working to build a generalization of type of things that had never been found before. And I just needed the existence of one set to prove that there were infinitely many. And I had the computer running, and it finally found a set. Unfortunately, I only had to print out that the set existed. It didn't actually print out what the set was, and I lost all the information. I actually knew what A plus A plus A was. So if the set was A, I knew the elements in A plus A plus A plus A, I think, and the elements in A plus A minus A minus A. But I didn't know what A was. And so the question is, can I deduce what the set is from knowing these things? Fortunately, I could just run the program again. It only took a few hours. So not a big deal. But you always want to be careful and think, what information do I need? There's been several times in my research career where I have later needed results that I did not initially think were important. So you want to figure out, what do you want to save? We are not saving the values of the iteration. That could be a big mistake. But if we're looking at large numbers, it's going to take up too much space. And so the count for 7, oh, I have to rerun it now, sorry. The count for 7 is 16. Now, one of the problems with this is, as you notice, it's printing things out in a line like this. If we did it as a list, it would be much better. You could then just print out the list at the end. If I take 29, 18 steps. If I do 19, 20 steps. Should we do one more? Anybody know the number I should put in? I'm sorry? 9. Not 9. I believe it's 27. Did you see how much this moved up? All right, so I'll go a little bit faster now. I hope the dramatic. And eventually, we see our old friend, 40, 20, 10, 111 steps. If you look at all the numbers around 27, you're not going to see anything as bad as 111. Why did it go up so much right there? How do you feel about the 3x+1 conjecture now? Is it possible to escape? Now, instead of doing the function f, what function could we have done instead? G. And so it's really easy to change this. What do I have to do to now use the function g?
Switch all f's.
Yeah, switch all f's to g's. In fact, there's only one f. Right? That's pretty easy. Now we started 27, and from 111 steps, it's now only 41. What we could do is we could go one step further. We could do print, and we could do function. And then there's probably a better way to do this. I will do current equals if function equals 1. I will do f of current. Otherwise, I will do g of current. And this gives me the way to choose which function I want to use. So I can now have either f or g, and I just have one program that's a little bit more flexible. There's probably a way to have Mathematica define a function in the very beginning. I can even I'll try that right now. Let's say maybe no, because if I define it over here, I'm still going to have to be doing a check every time I use. No, I think I would only have to do it once. I could do maybe h of x dot equals, and then okay, so I could do if function equals 1, it's going to be f of x. Well, I've used x as a variable in another, so I'll just do y. I'll do f of y, and otherwise I will do g of y. So let's see if this works as a definition. And now I would just do current as what? I just do it as now just h of current. And so now, if I do 1, this should hopefully give us 111. And what was the other one? 41? Any other number other than 1 will give me g. Okay, that's 41. And so what's nice now is, again, sometimes very small coding changes can make a huge change in runtime. I'm now only doing the if test once. Yes?
Can you pass the entire function in?
I probably could. And then, I mean, in some sense, I'm passing both f and g because I've defined f and g globally and not locally. I could have them defined over here and then just choose which one I want to use based on this.
But like as your variable, could you put like f as a variable function? Could you just pass it in and then just have h go equal function?
There's a good chance you could. I strongly urge people to try that and see if you can just put in some kind of letter. There may be some special way you have to code it so it knows that it's using it as a string name function, but I think it's quite likely you would want to do that. And since you probably want to do that, Mathematica probably has a way you can do that. I'm using the fact that I'm not a great programmer, but I know enough tricks that I can do some simple things like this. All right, so this allows us to investigate things. We could also have a list print, right? List print. And now what I can do is I will make list is empty. And then if print is 1 is this, if list print equals 1, list equals append to list and current. And in fact, I might as well start off with list just having start. And then at the end, if list print equals 1, print list. And then this will just print all of our stuff, and it'll be a little bit more concise. So here, I'm going to do G. I'm printing everything out as I go. It's painful. So now I will print out nothing, and it will just tell me how many steps it takes. And if I want to see the list, I'll just put a 1 over here, and that's much more compact. So now we have a way to start investigating things. How large of a number do you think we can work with? Who here is, a CS geek or a CS major? All right. What languages do you guys like to use? Python. Okay. So for Python and C++, how large of an integer can you put in?
4 bytes.
4 bytes?
There are larger data types.
Okay.
You get a little bigger.
Okay.
You could do shifty stuff above that.
Okay. So give me a number about how big you think you can get.
2 to the 30th.
2 to the 30th. Let's have a little bit of fun. Random integer. So random integer gives a pseudo-random number in the range from 0 to I max. So what I will do is I will do a random integer from 0 to 200. Okay? Just in case 2 to the 30th, maybe that's a particularly bad number to start the 3x+1 problem with. Yes? Right? What will happen if I start the 3x+1 problem with 2 to the 30? Boom, 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 boom. And if I use the function g and not f, whoomp, right? So, I have a couple things I could do. I could do 2 to the 30, and then it's not going to really be good. I could do 2 to the 30 plus 1. But maybe being one number away from the power of 2 is not truly generic. So I think as soon as I put in a random, I feel much more confident. 88 steps. Probably should have asked you how many steps you think it would take before we get there. But that's not so bad. So you said you can do about 2 to the 30th?
That's 2 to the 32nd is an int size.
All right.
So you can,
Let's do 2 to the 300. About how many steps do you think that might take? 2 to the 30th was about 88. Well, instead of looking at 2, since we're more comfortable, let's look at maybe 10 to the 30th. So Mathematica is dealing with a 100-digit number. The amount of time it took was not even noticeable. I can put a timing statement on these things. Essentially, it takes longer to hit Shift-Enter. Actually, do you know what the biggest timing part of this program is? Printing to the screen. The actual calculation goes, I think, much faster. And just saving things to the file. If I don't save things to the file, it'll be a little faster. So it took 235 steps to reach 1, starting at 10 to the 30th. What do you think I should do? Do you think it's always going to take 235 steps? Do you think it's going to take around 235 steps? You've got one data point right now, right? If you only have one data point, what's your best guess? 235, right? Let's do it again. 230. Let's do it again. 330. Ooh, huge difference now. 297. So, ooh, the 235, maybe that's low. 240. Oh, maybe it's not so low. 175. Oh my God, 175. What number is this? What would you like to do at this point? Do all of, okay. Yes, I would love to do all of them. I don't have the computing power to do all of them. Not on this machine, yes.
Do like, say 100 different ones and just like graph it?
Right, I might want to do a little bit more than 100. I might want to do maybe 10,000. But, you know, if I could only do 100, I mean, looking at how long it takes, this is not so bad. Right? So, yeah, a lot of this is trying to learn how to gather some input. So what we can do now is, if list print equals 1, let's do a little bit more of an analysis. Let's see. And so I always want to begin and end. End of list print equals 1. So here I'm printing out the list. What I can also do is, you know, print, I think it's average, nope, not average, maybe it's mean. Mean of list of list. Now print average is, what other information do you want? Those of you who've taken probability with me can speak up, but those of you who've taken stat, variance. Well, we don't really want the variance. Standard deviation is and then the last thing we can do is print histogram, and then it's list print, I think it's automatic, and I think probability in quotes.
This is all for the list that's generated by a single number, right?
This is all for the list generated by a single number. So now we're taking the number 346 ... It takes 169 steps. Okay, histogram is not valid data set or list of elements. And notice that we get the average is blah and the standard deviation is blah. Is that useful? So what we could do is we could put in a 1.0. And now when I run it, oh, it's not list print, it's list, sorry. Now it should work. And now we get, the average is 1.89 times 10 to the 28. The standard deviation is around 10 to the 28. What's going on? It's related to something that was said a moment ago. Are we calculating the right quantity? No, we're just calculating all the terms in the list. That's not what we want to analyze. Right? We want to analyze the count. We want to vary the count. We want to vary the starting seed. So what this is doing is it's studying the wrong thing. So what we might want to do is we might want to change this so that we would no longer have a start. We would have maybe a number of iterations. Num_do. And then maybe, you know, for n equals 1, n less than equal to num_do, n plus plus, and then begin, and then end. So this will be end of n loop. And so now I'm going to just quickly change the code a little bit. So count is 0. Current will be maybe start power. So we will do 10, sorry, random integer 10 to the start power. Okay? And now I'm going to kill all the list print stuff, and I'm going to kill the print stuff here. I probably should have saved the code before, but So I'll kill the list. And what I'll do here is, before we do this, I'll say results is going to be empty. And now n goes from 1 to num do in steps of 1. Count is initially 0. Occurrent is random integer. Well, we can have that global definition over here. We don't have to keep defining that again and again and again. We'll kill the print statement. And then while current is greater than 1, we apply our function, increase the count. We're not going to print anything. We're not going to save anything to files. We're going to try to make this a little bit faster. And then we're not going to print the number of steps it takes. And it's going to end the loop. And so now, we're going to not print anything out. And so now we want to just print the mean of results, the standard deviation of results, and then the histogram of results. And now, the hard part is now remembering what are the commands we want to do. So we want to start off with the number of things we want to do. Let's start off with 10, not too many. We want to start off with a power. Let's do 100. Oh, we need the function right, sorry. Iterate f. So we'll do 10 iterations, start off at 10 to the 300. Did I make a mistake?
I think you missed adding the count.
Oh, yes, thank you, yes. So right before we end the end loop, we finished the while loop. Now we want results equals, thank you, append to results count. Yes, thank you. That would be bad. So now we'll do 10 to the 300. And then function, we'll do function 2, we'll do the g function. Okay, here we go. So we did 10 iterations starting at 10 to the 300. So you would want to, of course, print something like this. Print, doing numdo runs starting at 10 to the start power. Okay. So 10 runs starting at 10 to the 300. Average is 2,338 steps. Standard deviation is 124. Let's do 1,000 iterations. All right. So now it's beginning to take some real time.
Could you speed it up by caching what you already know as you go? Like all the chains, once you reach a number you've already gotten to?
Good. So one thing is to save the results. What's the problem with saving results? It's a lot of memory.
It shouldn't be too much if it's just...
But the problem is, because the number's of size 10 to the 300, the odds that we hit a chain, is that high or low?
It depends. I mean, are you always hitting chains once you get low enough?
Once you get low enough, you'll always hit a chain. But how many steps will it take for you to hit that chain? If we're at 10 to the 300, now you have to manage a list that's extremely sparse. So there's a lot of really good technical things. So this took 22 seconds. If you had to guess, what would you guess for that curve? Maybe a bell curve. Is it normally distributed? What do you think the scale is? So we've got about 30 seconds left. So this is a good place to stop. I'll send you some of the code. I'm going to save this as a different file name so I can actually restore. Whoa. Code. Many. So what do you think would be the conjecture? So it's trivial to conjecture that it goes down to 1. What's the speed? If I give you a number of size 10 to the 300, about how many steps do you think it would take? So what I want you to do for Friday is I want you to work in groups, write some code. Think about how you would handle stuff like this. Mathematica is able to handle a number with 300 digits. When I was at Ohio State, I dealt with numbers with 100,000 digits routinely. If you try to put in 100,000 here, I think Mathematica will explode. How would you handle a 100,000 digit number? You actually know enough to do this. So I will send you more detail of things to think about. So I'm trying to keep the homework light. Most of you are never going to use this function in the rest of your life, but I want you to think about how you would approach a new problem. How would you approach something like this and work with a 100,000 digit number? Okay. Have a good day.